Welcome to this NPTEL lecture. Today we will see the numerical evaluation of antenna currents. Actually, earlier while discussing wire antenna for long dipoles, we discussed that the current distribution is approximately, or that time we said that it was sinusoidal, because if we are feeding the dipole at the center and the currents, conduction current should go to 0 at the two extremes, and at the feed point that should go to maximum. So, it was said that it will be sinusoidal, but people have found out experimentally also and also by other techniques that it is not exactly sinusoidal. Look at the top graph, it is for a lambda by 2 dipole. It is a thin dipole because the dipole's radius is quite small in terms of lambda, and here in the x axis is plotted the distance from the center. So, that means this is the central point and this is the top point, and the current distribution is symmetric in both the poles. So, you see that we have plotted the sinusoidal one by the red color, but actual current is not exactly, it is the maximum is not at the center, first thing, because peak is somewhere else, and also you see that typically it can be said exponential, but it is not exponential, there are deviations. And now, if this is have a profound impact, if we try to find out the input impedance of the dipole, because at the center you see that by sinusoidal thing, the whatever we will expect the current, that is not same. So, if we, because what will be the input impedance at the feed point, we will find out the applied voltage divided by the current. So, if the current is different, then the input impedance will be difficult. Basically, the near field effect is different for if we assume a sinusoidal distribution and a actual distribution like this. The second graph is for a lambda dipole, that means full wave dipole. Again you see it is a thin one. Here also you see that sinusoidal is as expected, but the peak is at a different point, and most importantly you see that here the center fade, at the center the sinusoidal current distribution says 0. So, that should give you input impedance should go to infinity, which is not the case. No no dipole gives you infinite input impedance. We have seen the input impedance is something like some complex term, but the radiation resistance is something like 73 ohms, so near about that, etc. So, you see that, but the actual distribution that is not 0. So, you can easily get the exact one. Now, how to get this type of exact current distribution, that we will discuss. Actually, so will today's topic is numerical evaluation of the dipole current. So, let us say that we have a dipole. Now, actually in the earlier discussions we always neglected the finite radius of the dipole, but actually if I want to make a dipole, it will be a cylinder. So, any practical cylinder will have a finite radius. I can keep it small, but that means on the surface there will be currents. So, currents will be distributed if the dipole is made from a perfect conducting elements or any practical elements, then there will be currents in the circumference, and so it is not always that the through center the current is going. So, that is one thing. Another is we are having a finite gap at the feed point. Now, that gap we do not consider, because we consider that the dipole's center is also at the center, but actually dipole center is a delta up and the delta down. So, that is not model. Today we will take that also into account, and so a dipole is something like this. And there is this gap. In this gap, we put, let us say, some feed whose job is to put the voltage generator. So, I can say that this voltage, let us say, in impressed voltage, and let us say this gap is something like delta. Let me call. So, I can say that from the central point to the top, this is L by 2. Similarly, so that means this length of the top pole, that is L by 2, the length of the bottom pole, that is also L by 2. Now, previously if I help you to recall that we have taken the current distributions while we discuss sinusoidal. We have taken that this is A z I naught sin k L by 2 minus z dashed for 0 less than equal to z dash less than equal to L by 2, and in the bottom half it is I naught sin k L by 2 plus z dashed minus L by 2 z dashed then 0. That was our earlier thing. Today we will see that for the center fed and finite diameter wire, this is not exactly true. Though we will say that, as we have seen, that sinusoidal typically we can say, but it is not exactly true. So, if you want the radiation pattern, if you want the input impedance etcetera to be exactly determined, because that is very necessary for circuit matching etcetera. So, this is true. So, there are two techniques more or less similar, but there is a bit difference. So, those techniques we will see. The first one scientist Helen, he first found out this. So, that is why this formulation of the analysis, that is called Helen's formulation, which we will see. So, this is not our current distribution. We now say that we do not know what is the current. So, we will determine the current. So, we will write the Helen's formulation. It is a very well known technique, very much used. Actually, previously people used to have some iterative techniques to solve that, but today with the advancement of various numerical techniques, that also we will discuss probably in the next lecture, that there is a technique which is very much appropriate for this type of current distributions problem, or in case of determining currents for scattering problems or any radiating problems, that is called moment method, that is an integral equation method, that also we will see. So, this Helen's formulation has assumptions. So, there are first one is that the radius is finite radius of the radiating structure. So, we will say usually they call that the diameter that is greater than 0.05 lambda, then the dipole is long. So, L is greater than A, and I am not writing much greater because this is applicable for all these cases, but L should be greater actually, and also we require that A should be much less than lambda. Now, this actually what happens if I have a practical cylinder like this. So, there will be currents in the sides, also in these top caps of the cylinder, top and bottom caps there will be current, but by this assumption actually we are neglecting that cap. So, we will say that only the current is on the cylindrical surface, not on these planar caps. That is why these assumptions. Now, on this we will put the boundary condition. What are the boundary condition? You see always these boundary conditions, that one is, since this is made of perfect conductors. So, we will say the first boundary condition is total tangential electric field will be 0 on cylindrical surface. Cylindrical surface. This is always true, plus please remember here it is not true, in the gap it is not true, but on the cylindrical surface. The second boundary condition is obvious, that our current, we do not know the current yet, but at the end points this will go to 0. These are the two boundary conditions sorry, we will enforce. Okay. So, what is Helen's formulation? As we have seen that since this is a perfect conductor, so we assume that there is only electric current. So, we can say that M is equal to 0 here, and our current density J, that we will write as Jz. Now, this is an assumption actually that I will come that. So, Helen's formulation says that current is typically going like this. Actually, it is an equivalent thing, there are currents here. So, he assumes that the, since it is a symmetrical structure, so summing that I can have a equivalent current on the axis of the things. So, if I have this, then we can write that what is the electric in terms of the applied electric field E A. Please remember those A's come from that magnetic vector potential while we discuss the general solution, that thing. So, we can write E A is equal to minus j omega A minus j by omega mu epsilon del cross A. On the cylinder, on the cylindrical surface, I can say applied electric field is 0, because we are not applying any electric field there. So, this boils down to that, I will not go, this boils down to that vector potential satisfies this differential equation. This we have seen many times. So, we will have to solve this equation. Once we know the vector potential, we can easily find J. So, that will be now we can say that J j is symmetrical in Z or Z dash. That means J Z Z dash is equal to J Z minus Z dash, because of the structure the excitation is symmetrical. So, bipolar excitation. So, this tells me that A z is also symmetrical in Z dash. That means A z Z dash is also A z minus Z dash. So, one solution, because A z is satisfying this differential equation, one solution is A z A z z is equal to minus j mu epsilon A 1 cosine function plus to have this symmetry, and this you can put it here and see that it satisfies. This term is coming due to this k, presence of k, you are getting this term. So, A 1 B 1 are unknowns. Okay. So, A 1 and B 1 are constants to be determined from boundary conditions. I have two unknowns, I have two boundary conditions. So, I will be able to do that. Okay. Now, I will come to this solution a bit later. First, let me evaluate these. So, now let us look at the gap. Now, at the gap. At the gap, let me see, this is the structure. So, at the gap, the applied voltage is V I. So, there we can write the differential equation del square A z plus del z square plus k square A z is equal to, or I can write d because there is only one. K square A z is what? If you put it, j omega mu epsilon E A. This is the at the gap. Now, let us integrate this whole thing over the gap. So, we are integrating it minus delta by 2 to delta by 2 square A z d z square plus k square A z d z is equal to minus delta by 2 plus delta by 2 j omega mu epsilon E A d z. Okay. Now, I can easily integrate these are all constants. So, it is basically, or let me write it, that right hand side is j omega mu epsilon minus delta by 2 to delta by 2 E A d z. What is that? j omega mu epsilon into what is E dot dl, this is a line integral, minus vi. Now, let us look at LHS. So, LHS is, I can say that if I integrate it, then del square Az del z square plus k square Az k square Az dz minus delta by 2 to delta by 2. Now, this I should take that this is happening at limit z tending to 0. So, this will be limit z tending to 0. The first one will be that del Az del z, one integration, plus k square minus delta by 2 to delta by 2 Az dz, whole limit. Now, I have the expression for Az, this is the expression. So, del Az you can put, and also this one you can integrate. So, that will be limit z to 0 j mu epsilon k A1 sin kz minus B1 cos kz plus k square minus j mu epsilon minus A1 by k sin kz plus B1 by k cos kz. Is equal to j k mu epsilon. These are simple integration sign functions. So, you can do yourself, but still for helping you I am writing it. Now, you enforce the limit. So, it will be minus j k mu epsilon 2 B1. So, you can, this is your LHS, RHS we have found, equate these two. So, we get minus j omega mu epsilon 2 B1 minus j omega mu epsilon Vi, that implies that B1 value I got as Vi by 2. So, B1 I got E1. Now, knowing this, I know the second boundary. So, this is the first boundary condition. The second boundary condition is that you put it there BC2. So, that will that I j z dashed is equal to 0 at z dashed is equal to plus minus L by 2. So, from this A you now find out I, put that. So, that will give you this you can take as an exercise, this gives you A1. So, that means now we know A1 B1. Okay. So, that means I know the solution. So, from there we have, so that means A we know, and already previously this expression we have found that if we have that in terms of what is the relation between A and Iz, that is an integral relation. In the previous we have found it that if I have a only a linear current, then it is a contour integral Ij x dashed y dashed z dashed e to the power minus j k r by r dl dashed. So, also I have the solution of A, that A is in our case is minus j root over mu epsilon A1 cos k z plus B1 sin k z. So, these two are equated. So, this one I can put the thing minus L by 2 to plus L by 2 I z dashed e to the power minus j k r by r 4 pi r d z dashed is equal to minus j by eta A1 cos k z plus B1 sin k z. Okay, this mu and this gives you this impedance. Now, this equation, now you see the right hand side is fully known, A1 B1 I know. So, I will have to find Iz dashed, but unfortunately Iz dashed is under, or it is an integrand of this equation. That is why these equations are called integral equations. So, this formulation is an integral equation formulation, because this is unknown and this is under an integration, or this is a integrand to an integration. So, that is why it is an integral equation. So, this is the definition of any integral equation, that if the unknown is under in the integrand of an integration, then that is called an integral equation. So, this needs to be solved. Actually, this equation is called Helen's equation. This is a famous equation. Now, this equation, if you can solve, that means integral equation solving, then we can find the current distribution. Actually, we will see later that how to solve this equation. Okay. So, this we will see that another formulation is also very much used, and that has certain advantages. The advantage is that actually the we will finally see, if I want to solve it by moment method, then I need to inverse. Actually, this one, to find this I need to inverse something. So, one order less, because here this A1 also is an unknown which needs to be solved, because we are seeing the vector potential. Actually, this A1 is a confusing thing, because this is a vector potential A and this is a unknown A1. So, now, so order of integration, the inversion, matrix inversion, we will see n plus 1, that we will discuss. So, that and also the generator, that is a voltage generator, but other types of various feeds that cannot be analyzed by this formulation, because it always assumes that there is a voltage generator or spark gap generator there. But another general feed thing, that is called Pocklington's formulation, that is also integral equation formulation. So, we will see now that Pocklington's integral equation formulation. Again we have that cylinders. Here the current density is on the surface. So, the first assumption of this is the current density J j is on surface. So, it is called K z. That now the second thing is this surface current density K z is circumferentially uniform. So, we can write that I z at a point z dash, that will be 2 pi a K z z dash. So, here it says that it is uniform circumferentially, and the third thing is important. It is a refinement from Helensey, that there is a scattered field. So, the thing is E z is a scattered field created by the equivalent currents in the wire actually J z is on surface here, but here it says that this circumferential current, I can finally take an axial current equivalent to that, and that will scatter the field. That field will call E z thing created by the equivalence current in the wire, assumed to be located at the axis of the cylinder. So, remember, we are not saying that the current is that, current is circumferentially distributed, but equivalent thing that we take, we can easily take this uniform thing, what is the equivalent current, that is at the axis, and because it is a symmetrical structure, and that scattered thing is this. Now, again we can say that M is 0, the magnetic current, and current density is given by this AZ So, same as Helen's thing. So, we will have to solve this equation del square AZ plus del Z square plus K square AZ is equal to j omega mu epsilon Ez. So, you see in Helen's equation we said this is 0 everywhere except the gap, but here we are saying no, there is also a scattered field because of this. Obviously, there is an applied field at the gap. So, this is that is why more than general, and so we can now solve this from the earlier thing. So, I can directly go to this Pocklington's formulation that. So, we can ultimately write this L by 2 I z z dashed, or let me say that what will be the solution of this thing, its solution will be obviously in general this we have already seen earlier. This differential equation, its solution is this, and now specializing these for our all those assumptions, we can write that this is del square del z square plus k square e to the power minus j k r by 4 pi r dz dashed is equal to j omega epsilon E z s and z directed z variation. Now, what is E z s? We know at the cylinder surface the total tangential electric field should be 0. So, there since both are same, I can write that E z s z dash plus E what I will write E z incident means what is applied, they should go to 0. That means, I can always write E z s z dash is equal to minus E z I z dash. So, this if I put here, I get, or I can write here that this is minus j omega epsilon E z I z dash z. Okay. And also what is R? R is nothing but if we go to cylindrical coordinates, rho square plus j minus z dash whole square. So, this formulation is called Pocklington's integral equation formulation. You see, it is a similar structure, integral equation, because this is unknown, this part is known. Actually, from the given excitation spark gap, if you say I know what is E z I will calculate. If any other type of feed, I can find that. So, E z is in my hand, but it is known. So, this side is known, this side is some operations, this function is known. So, I need to solve it. So, this integral equation for both Helens and Pocklingtons people have solved, and then there are various techniques. One of that I said most efficient one, most easy for computer implementation is moment method. That we will discuss a bit of moment method in the next class, and then we will see how to solve this equation in the next class. Thank you.